All right, today we are diving deep into the heart of modern electronics. We're going to go and uncover a secret, a hidden property of one of its most basic components. Yep, we're going on a hunt for a hidden capacitor. So let's just kick things off with a little bit of a puzzle. What in the world could a simple one-way street and the complex tech inside a radio possibly have in common? I know it sounds a little weird, but the answer is tucked away inside a tiny electronic component and a little bit of quantum physics. Just stick with me and I promise we'll connect all the dots. Okay, so meet the hero of our story, the PN junction diode. At its heart, it's basically an electronic valve. Its entire job is to enforce one simple rule. Current can flow through it, but only in one direction. It's literally the one-way street for electricity. So how does this one-way valve actually work? Let's peel back the layers and take a look at how it's built. It all starts when you fuse together two specially treated pieces of a semiconductor, usually silicon. One piece is what we call p-type, and it's got a bunch of holes. You can just think of these as empty parking spots for electrons. The other piece is n-type, and it's jam-packed with free electrons, all just looking for a spot to park. Now, when these two materials meet, it's kind of like musical chairs. The free electrons from the N side immediately rush over to fill all those empty holes on the P side. This little flurry of activity creates a really thin zone right at the junction that has no free charge carriers left. It's been depleted. We call this the depletion region, and it acts like a barrier, a closed gate, that stops any more current from flowing. Of course, a closed gate isn't all that useful by itself. The real magic of the diode is that we can actually control this gate. We can open it and we can close it just by using an external voltage. And this whole process, it's called biasing. And there are basically two ways to do this. If we apply a positive voltage to that p-type side and a negative one to the n-type, we call that forward bias. This actually pushes the charges together, shrinks the depletion region, and boom, the gate is open. Current can flow. But if we flip the polarity, negative to the P side and positive to the N side, well, that's reverse bias. This pulls the charges apart, makes the depletion region even wider, and slams that gate shut even tighter, blocking the current. And in forward bias, it only takes a tiny little push. We're talking about 0.7 volts for a standard silicon diode to overcome that barrier. Once you give it that little nudge, the gate just swings open, the resistance totally plummets, and a large current can flow through, no problem. So, we know that applying a voltage backwards, reverse bias, closes the gate. But what if we keep pushing? What if we really lean on it? I mean, every valve has a breaking point, right? And this is a really important question. If you apply enough reverse voltage, that diode will eventually fail, and it will start to conduct electricity backwards. But this isn't just some simple break. No, it happens in two very distinct and honestly pretty fascinating ways. These two breakdown methods are called Zener and avalanche. Zener breakdown tends to happen at lower voltages in diodes that are heavily doped or treated with impurities. Avalanche, on the other hand, occurs at much higher voltages in more lightly doped ones. But the real difference, the key, is how they break. One is this really subtle quantum effect, and the other, well, it's more like a violent chain reaction. The Zener effect is just pure quantum mechanics at work. See, in a heavily doped diode, that depletion region is super thin. So when you apply a reverse voltage, the electric field gets so incredibly strong that electrons can just tunnel right through the barrier. It's something that just shouldn't be possible in classical physics, but in the weird world of quantum mechanics, it's totally normal. Avalanche breakdown is, well, it's a lot more dramatic. In a wider depletion region, a single charge carrier gets accelerated by that high voltage until it's got enough energy to just slam into the silicon lattice. This collision knocks a whole new electron-hole pair free. So now you have three carriers, all accelerating, all causing more collisions. You see where this is going? It's a cascading chain reaction, a literal avalanche of charge that creates this huge reverse current. Okay, so we've got a one-way valve that can break in some pretty interesting ways. But remember why we're here. We came looking for a secret, so let's get to it and reveal this diode's hidden identity. So think about it. A capacitor's job is to store charge, and it just so happens that a diode's depletion region also stores charge. So you might be thinking, hey, can we just treat it like a simple parallel plate capacitor? Well, as the source material puts it pretty bluntly, no. So why not? And the reason is absolutely crucial. See, in a normal capacitor, the relationship is linear. You double the voltage, you double the stored charge. It's simple, it's predictable. But in a PN junction, that relationship is nonlinear.
The charge doesn't scale nicely with the voltage, and that's what makes things so much more interesting.
This whole complexity actually gives rise to two completely different types of capacitance. First up is junction capacitance. This comes from the charge that's stored right in the depletion region itself. This one is the main character when the diode is in reverse bias. The second type is diffusion capacitance, which comes from a different effect entirely and really takes over when the diode is in forward bias. Let's really focus on that junction capacitance for a second. We can think of it like a parallel plate capacitor, but with this really cool twist. The plates are the edges of the P and N regions, and the separation between them, that's the width of our depletion region. And since we already know that reverse voltage changes that width, well, get this. That means we've just created a capacitor whose capacitance we can change just by tweaking a voltage. A voltage-controlled capacitor? I mean, that has to be useful for something, right? You bet it is. This is a brilliant example of how a really deep physics concept can lead to some incredible everyday technology. Let's see how this whole thing comes together. So engineers, being the clever people they are, created a special component called a varactor diode. Sometimes you'll hear it called a varicap. Its entire reason for existing is not to be a one-way valve, but to be used as a tiny, electronically adjustable capacitor. It's designed specifically to harness that junction capacitance we just uncovered. So how does this little thing actually tune your car radio? It's really elegant. The varactor is put into a tuning circuit. When you turn that knob or push the button to find a station, all you're really doing is changing the reverse bias voltage that's applied to the varactor. This changes its depletion width, which in turn changes its capacitance. And changing the capacitance in the circuit changes the specific frequency it's tuned to, letting you jump from one radio station to the next. And there you have it. That's the answer to our puzzle. The one-way street, the diode, hides a secret capacitor. And by controlling that tiny capacitor with a simple voltage, we can tune a radio, a microscopic physical property connecting two things that seem like they have nothing in common. It really makes you wonder, doesn't it? Our entire world is built on these tiny, elegant principles of physics. So what other invisible forces and hidden properties are at play in the technology we rely on every single day? In the phone in your pocket or the computer on your desk? That's definitely something to think about. Thanks for joining me.